China and the United States are facing off to control the two-dimensional material market. Examples of that are graphene, silicene, and molybdenum disulfide. The reason why they're so important is that you can create a layer of this material that is only 1 atom thick, and it would still hold. These materials show the most promise in electronic devices and also nanotechnology. We are talking iPads that could be wrapped around your wrists, laptops that could be modern-day supercomputers. So of course, these two great powers are fighting to see who can dominate it. Right now, the industry is very small, only at about $526 million. It's projected to go about 8 times that value by 2031. For those of you who are a bit techie, you know that graphene is by far the most popular one. It's by far the most extensively studied since its isolation in 2004. The European has set up the EU graphene flagship, which is about a $10 billion investment into researching this technology. Its commercial applications have already been put into batteries, supercapacitors, and composite materials for enhanced properties. But I have to tell you something. I've known about graphene and what it could do for the world since 2009. I invested in it. I doubled or tripled my money, but it didn't take off the way everyone else was expecting. Why haven't we launched into this ideal graphene tech related scenario? Graphene is just made from carbon, so why don't we just get it from coal or pencil material? Because even though carbon is so abundant, it's very expensive to turn it into a nanomaterial. It's extremely sensitive to oxidization. Because of its high surface area, it's prone to chemical reactions. Now pay attention to this one, because I think it's one of the most important. Band gap absence. Band gap distances are what covers the differences between a conductor, a semiconductor, and an insulator. If there's no band gap, something is a conductor, potentially even a superconductor, which means electrons flow freely. If something is an insulator, there is a very large band gap and it doesn't allow for a lot of conduction. What's in the middle? Semiconductors. You figure that out. We all know that there's a huge battle between EU, China, and the United States as to who gets access to the best semiconductors in the world made by Taiwan. And that is why we don't see graphene at the forefront of technological innovation. Starting to look like there may be more potential in molybdenum disulfide, which is why, aside from graphene, it is among the most researched and invested 2DMs. Remember what I said about graphene not having a band gap? Well, molybdenum disulfide has one that can be manipulated, even in its monolayer form, which means 1 atom thick. That could still be demonstrated, which means it can be used as a semiconductor, but also as a superconductor. While graphene has a lot of qualifications as a superconductor, it's not as malleable as molybdenum disulfide. Let's just call that MOS2. And MOS2 is better for digital electronics, photodetectors, flexible electronics, field effect transistors. I don't want to get too technical, but it looks like that's a much bigger win for molybdenum disulfide because field effect transistors are used in both superconductors and nanotechnology. That's the kind of stuff we would see in maglev trains. Those are the ones in China and Japan where the train is actually slightly hovering above the track. While the United States and China both seem to be leading in research towards graphene and other two-dimensional technologies, it looks like China is ahead of America when it comes to patents and money put into the research. The two countries that have pioneered the most when it comes to researching molybdenum disulfide appear to be the United States and the UK. If you look further into it, you could see that the United States and the European Union have pioneered the most research when it comes to any kind of two-dimensional material. Two-dimensional material industry is in its nascency, to say the very least, and we don't know if graphene or molybdenum disulfide are going to win, or maybe it's going to be something else like silicene or silica glass. Whenever research into any of these two-dimensional materials seems to solidify some useful results, then we are going to see a transition similar to when vacuum tubes were ditched for the transistors. I'm the Geo Husar, and I will give my next economics post in about 2 days. Thanks for watching.